Okay, let's let's continue this look at the dynamics of gradient descent and the type of solution. This is literally ongoing work, and so there are, I'd say, likely errors today, and so help during this class. Don't hesitate. Help is welcome. You're likely to be correct if you think there is an error. Okay, so I want to repeat some of what I said at the very end last time, because it was a bit quick, and look at the dynamics induced by gradient descent, first in the square loss case for linear networks, multi-layer, deep networks, and then same thing for the exponential loss, general losses like the logistic and the cross entropy that are used typically for classification. And so let's start with the square loss, and we are interested in convergence and which kind of solution it converges to, stability of those solutions, and one reason is just because we'd like to understand how these optimization procedures work, but also because this gives us keys to other questions about complexity and control of norm and so on that Sasha spoke about last time, but this would be how this actually happened in optimizing training deep networks. So first of all, let me, in terms of the notation, just to remind you, our function is, in general, a deep neural network. So it will be the matrix at the top layer, let's call it K, no nonlinearity at the top, for instance, in this case. This is a matrix. At the top, we have just one output in this cases I treat, so it's a vector, and then there are other layers, and the output of each layer goes through an RLU that I indicate as a sigmoid, and so there will be, let's say we are at the second layer, and here is a real matrix, and this is applied to the output of the first layer, which is also a real matrix which works on the input xj. Okay, so K layers in this way. And we'll speak about the Jacobian of this, which is the vector of first derivative, where, as I said last time, the weights are indexed by this multi-index ijk. And the Hessian will be the matrix of second derivatives, which is indexed by, again, these two multi-indexes, ijk and abk prime. Okay. For instance, I can ask you, what is the second derivative dvikk and dvjk Jmk. Do you see this is when you take a derivative with respect to layer k, or the vector of derivative with respect to layer k, that function does not depend on the weights of layer k anymore. So if you have a one-layer networks, for instance, k is equal 1, the second derivative is 0, automatic. Okay, another thing related to notation, as I said last time, I'll not speak more about this apart this, but typically in gradient descent you are looking for time derivatives of the weights, and this will be equal to minus the gradient of your energy function or loss function L. And here you typically have a learning rate, say, function of time. In real use, the learning rate is supposed to decrease slowly with time. In the rest of this, as I said already, I will neglect this, but the reason for having a learning rate, the decreasing of time, is the following. If you have, consider this very simple dynamical system, one-dimensional, is gamma t x equals 0. So the solution of this is this is the initial condition, the x at time 0, and then you have e to the minus gamma t in time from 0 to this t here, okay? Now, in order to have convergence to independent of the initial conditions to the stable point, which is 0, you want to have the integral of gamma t in the t going to infinity as time goes to infinity, because in that case the exponential will be 0 and the initial condition effect will disappear. So you want this and on the other hand, often you have noise in your weights or in your system. So in fact, you are dealing with an equation where you have something like this. This mt is some noisy, time-dependent term, and you'd like to have the gamma t and t equal 0 for t going to infinity. For instance, discretization is a noise in this continuous formulation. So if you want to get rid of the discretization effect, then you want gamma to go to 0. So you have this trade-off. For instance, a constant A in the equation above, which would be the standard classical one, satisfy the first condition, because the integral of a constant the time goes to infinity, the time going to infinity, but does not satisfy this one. So you would like something that is almost constant, but actually goes to 0, and the integral goes to infinity. Something like 1 over square root of t, for instance. Okay, that's the reason for a decaying gamma. And you need this especially when you do discrete calculations. In the continuous case, no noise, continuous, you don't actually need decrease A. All right, so let's consider what are called gradient dynamical systems. These are exactly the ones induced by GD. They are the dynamical systems, so differential equations that derive from the gradient of some scalar energy or loss function like this. And as I said, I'll neglect the learning rate. And in the square loss, this would be typically, we saw that already, the sum of, for anyone, for over all the data point of the loss of each data point. In the square loss case, in the square loss, Li is equal to f of xi. This is the network minus the label, in this case, the real value of fxi. And we're really interested in characterizing the stationary point or equilibrium point when this is when gradient descent stops. In other words, when w, the time derivative, is equal 0. Okay. And so this can define a point maybe at infinity when this happens, when the derivative is 0, and we are interested in characterizing whether this stationary point are minima, stable minima, or not. And as I said last time, this is typically done looking in one dimension at the second derivative, in more than one dimension at the Hessian matrix that tells you whether you have a stable or an unstable stationary point. And here is an example, for instance, for the square loss of what happens typically in could happen in over-parameterized deep networks. This would be a loss function, an energy function that is convex, quadratic, for instance, in one of the two weight parameters, but is degenerate in the other one. Okay? So you have flat valleys here. In that case, this is an extreme case in which not only the second derivative along that direction, along W1, are 0 at W2 equals 0, but all derivatives can be 0 in that case. And so let's go back. What we can say in this case, and in this case, let's start with the linear one-layer networks. In this case, our f of x is simply, there is no RLU. It's simply a vector. This is a matrix of just one row and our input xj. So let me write it like the transpose of the vector w, and here I will have the vector x. So this is a dot product. And then if I have my my loss now being again I equal 1 to n of yi minus what I might write explicitly here. I'm assuming there is a summation over j, and then I have that the dot product of w, let me use the matrix notation here, is to sum of the errors, let's call just without the square, I call it, is the error for point, let's say I, sum over I, and then I have, it's getting confusing, this would be the j component of example I, okay? So this would be the gradient descent equation. There is a minus, and suppose if I look at what this is in y equal wx. This is now, I'm rewriting this as a matrix. All the y are a matrix with the y yi as different columns, one row, and then I have W is the set of weights, which is a vector in this case, and X is again a matrix with all my examples. So having W dot 0, so a stationary point of the gradient, 1 j equals 0, implies that all the EI are 0, and so the W that comes out of it is W equal Y X pseudo inverse if it exists, or the inverse if it exists. Now, suppose that I have over-parameterization. So in that case, over-parameterization means that n, the number of data points, is less than the dimensionality. So I have fewer examples than components in the X. And this is the case where, of course, the inverse of X does not exist. X is not a square matrix. And in this case, I have a degenerate situation in which if I look at the solution of the minimum of the least square problem, I have an infinite number of solutions. I have an infinite number of choices for W, which put the error to 0. And choosing among them the pseudo-inverse is the choice of choosing among the infinite number of solutions that exactly satisfy the minimum, choosing the one that has the minimum norm. And you can see this in what happens in terms of the gradient, because what happens in the gradient is that if you have components J in the weights, which are not in the span of the xj, you will those components are not updated during gradient descent. So let me see this in a different way. We can if you look just at the Hessian of, in this particular case, in which you have over-parameterization, we have that the Hessian of L is equal to the sum over n of this let's say I n. This is same as the sum over the example of the autocovariance matrices of the example. Now these are rank 1 matrices. It's the outer product of a vector with itself. And so rank 1 means that if you have dimensionality d of these vectors, then you have one eigenvalues which is not 0 and d minus 1 eigenvalues which are 0. So the Hessian is degenerate. This essentially says that this is a situation in which you have a flat minimum, a lot of choices for your W, an infinite number of choices is degenerate, and but
say H, not L.
no, this was H. Yes, thank you first error. It was not a big one, but please keep going. This is the Hessian of L. So we can play this trick in this linear case, square loss. Take the L I had before, the sum of the square over the example, and add a regularization term, which will be a sum of the square of each of the weights. So now in this case, I get the gradient descent equation that are now minus, again I have the errors here. I have component j for example n, and then I have the derivative of this, which would be 2 lambda w1j. And so now, if I put this to 0, this now has a finite time solution, and this would be equal to, let's put the half here, equal to lambda w1j. And by the way, this term here in the deep network literature is called weight decay. So weight decay is exactly equivalent to a quadratic regularization term. And so so now the Hessian of this is, again, I had the sum over n of x, so this will be indexed, say, by I and j, xi, xj, this is n. And now I have lambda or 2 lambda, and this would be the second derivative, the diagonal element, dij, delta ij. And now this is a semi-positive definite. So it has one positive eigenvalues, but 0 eigenvalues. But together with this is now positive definite for any lambda, as small as you want. And so this says that for arbitrary small lambda, you have a stationary solution, an equilibrium point, and this one has the property of being the solution of minimum norm. You are minimizing this, you have a solution that you're minimizing the error in the least square sense, and you have a constraint on the norm if you look at the loss function you're minimizing. So essentially, this tells you that for lambda going to 0, you are recovering the pseudo-inverse minimum norm solution. Okay. So, interestingly, there is this other argument that is fully consistent with with this, which is that, strictly speaking, you don't have to add the regularization term. This is, and in fact, the argument here says you can add an arbitrarily small regularization term to get this result. And so the other argument is that if you use gradient descent, you are the linear network case, square loss. You are converging to the same solution that you have for lambda going to 0 with the regularization term. You do this without the regularization term. If you start from almost 0 weights. And the intuition is that you have the general direction in the weights, but gradient descent will not change those directions, in this case of the linear system. So they will stay at 0. And so you are changing only the ones that are affecting the error, but not the ones that don't affect the error. And so you are getting to a minimum norm solution. In terms of what you're doing is really, it's like a search. Suppose you start from, in the space of parameter, you start from 0, and you are a search in which you're expanding the ball, the radius of the ball, of the norm of the W. And you're searching larger and larger norms. But you are not increasing the norm of the weights that don't affect the error. So the condition for, first of all, not every optimization technique has this property, essentially to get into the regularized solution in the limit of lambda going to 0. Not in general, they don't, but gradient descent does. And let's see, I have here a couple of examples. First of all, this is just a restatement of what I said. Both gradient descent and stochastic gradient descent converge to the minimum norm solution for linear networks and square laws. And here you can see an example in which you have a linear network. In this case, it's not degenerate. So the Hessian is positive definite. Everything is fine. You don't need a regularization term. You don't need gradient descent. You converge to a minimum of the empirical loss. You will have some test error on a separate test loss. If you perturb your weights after convergence, you will see that your training error gets larger, but then goes back. Because this case is not degenerate. The Hessian is positive definite. Your stationary point in the gradient is stable, comes back. It's like you are in a stable ball. You move the stable hole here, and you move your ball, your weights, and they come back to the equilibrium point, despite perturbation. This is equivalent to having a stationary point which is invariant, independent of initial conditions. And on the test error, the same thing Okay. This is what happens instead in the case in which you have a degenerate Hessian. So now you are converging to a kind of pseudo-inverse solution. You have some overfitting, in the sense that the test error for asymptotic time is worse than it could have been at some earlier time. The norm of the weights increases up to a certain point. And now what you would expect. In this case, as I said, the Hessian is degenerate. You don't have a regularization term. So from the description I said, the gradient descent should converge to the pseudo-inverse if it started with zero initial conditions. Now suppose I perturb the weights after I reach. What do you expect in this case? In the previous case, we came back to the same equilibrium. And in this case, just a guess. Will it be affected by the perturbations or not? This is the degenerate case, right? It's like you know, you are in a situation like this. You are here, and now I perturb, and this direction will come back, but this direction, no. So it's like having initial conditions that are not zero. And in fact, if you do this, what you see is two things. Let's start here. You converge, you perturb. The training error goes back to zero. Of course, the directions that are important for the error come back. The test error increases. Before it was flat. And the total norm of the weights increases. These two things are related to what Sasha was saying last time. So you are increasing the norm because of the perturbation. You are not increasing the margin because you are really increasing the norm of the direction that don't matter for the error.
Can you give some intuition why the L2 norm should increase? Because if we're given the example
of the weights.
Yeah, why would the weights increase? Is the perturbation like biased to like positive
No,
in some way? Or?
no, but it's random. So this is it's basically a random walk. Think of I perturb W1 and W2, right, in a random way. So this W2 will return to zero. Sure. It's like a spring. W1 is Brownian motion. You know, perturbation after perturbation. And so it will get, in the average, farther and farther from the origin.
Maybe I'm not familiar with Brownian motion, but I would expect that.
It will tend to increase. The variance will increase with time.
Because maybe a comment is useful.
Yeah.
So your intuition is kind of like that you're starting from some point and you're doing random walk around it. In 2D, your intuition would be right, that you will come back to probably the origin.
Eventually, but
in higher dimensions, random walk never gets back to the origin.
Okay.
Probability is zero.
Okay, so that would explain. So in this particular case, like right over here with the actual image, my intuition would be right. It's just that in higher dimensions, it's like in this V shape with just weight
The
one, weight two.
perturbations that are random would probably
Yeah.
eventually maybe hit zero again.
Sure.
You don't know.
Yeah. Okay. Thanks. That clarifies it.
Yeah, the average would be zero, but the variance would increase with time. Yeah.
Why the test error is correlated with the norm of the weight?
Say again?
Why the test error increases as the norm of the weight increases?
Why the test error increases? Well, that's up to Sasha, right?
Well, this is a linear case.
Yeah.
You can probably write out the exact formula. And there is a component that's perpendicular to the data. It makes no difference in your predictions, but you pay for it. The norm.
But just in terms of even the complexity and, norm, complexity, and margin, these are, you're increasing weights that don't change the margin or the accuracy, right? They don't do anything to the error. So the norm increases, the complexity of the function increases, and your error, of course, does not improve.
Yeah, I think that's a valid point.
Because it's not classification, you mean?
So the question is, what is the test distribution that you're using? What is the test distribution that you're using? The test error.
It's on a test set. Out of sample, right? Not say what.
It's not, I think it's a valid point. It's not immediately clear why that should be the case that you're paying for the test error.
Well, if you look at the generalization bounds, these would seem to suggest that the bigger the complexity of the function, the worse the generalization bound. You have the same training behavior, so you expect that the test behavior has to get worse.
If you're judging from the upper bounds in terms of the random upper averages and the margin, then that's consistent. But it's not a proof that it should.
Yeah, my argument was in terms of the upper bounds. Was your question about whether upper bounds would be valid or?
Yeah, I'm just wondering, is test error necessarily correlated with the norm of W because they sort of increase at the same time?
Yeah, it seems perfectly consistent with the upper bounds.
So this would also suggest that random initializations can also be harmful for this case.
Say again?
The initialization, like the initial conditions, will affect a lot in your generalization.
Yeah, in this case, yes. This, perturbation. What's happening despite looks like there are many perturbations, but in fact, there is enough time for the gradient, the dynamical system, to converge back. The training error goes back to zero, right? So each time the perturbation is really like starting from a new initial condition, which is not zero, right? So this means that this shows also that it's in a situation like this, it's important to start from zero initial condition. If you start with all the weights are large, you will have a network that has an error which is not optimal. You're not going to converge to the minimum norm solution.
I guess the point is that you've only seen a subspace from data. If you have some extra component that you haven't seen in the data, you're just hallucinating that component. Right? So now the test comes, and in the space where you have the data, you've learned something. But in the particular, in the orthogonal component, you have no idea what's happening, so you should be paying for that.
Yeah. Okay, this is, I think this is summarizing saying again the same thing that, see,
Just for perturbation at some point.
yeah, it's essentially saying you have increased the norm because of these perturbations, or the norm of the weights, the ones that are not influenced by your training data. And so your training error goes, of course, back to 0. But the weights that are not influenced by the training error, the general direction, don't change, remain up there. And your test error remains up there. Okay. I think here there is this just a remark that when you run something like so this is a situation in which you have a linear network in which the features are a lot of monomials, and you're fitting a nonlinear function, but you have very few examples, much fewer than the dimensionality. So it's a degenerate case, but the pseudo-inverse seems to be doing well even when you have many more parameters than training data. Right? So this is, again, a case of over-parameterization. Is again making the point that we heard in previous classes, that is not the number of a parameter by itself if you can control in some way the complexity of the function. In this case, you control the norm by gradient descent. At some point, things breaks down, probably for numerical reasons. Okay, and just for your information, I'll not spend time on this, but the same type of things, the same results are true also for networks that are multi-layer but linear. You have some interesting degeneracy in the sense that you can choose the W1 weights in any reasonable way, and W2 will adapt to it, and vice versa. But so for all these cases, if you have a regularization term in your loss, then you have a stationary equilibrium which is hyperbolic. This means the Hessian is positive definite, is stable, does not depend on initial condition, will be robust for perturbations. But I can get to something which is equivalent to the limit of lambda going to 0 of that situation, so the lambda going to 0 in the regularization term, if I do gradient descent starting with 0 initial conditions. I can get to the same solution. In that case, it will depend on the initial conditions, will not be robust to perturbations. As I said, so that's true for linear and multi-layer linear networks. This is another example of doing comparing the effect of having a regularizer with lambda, and in the case of not having a regularizer, then essentially the role of lambda is played by early stopping. And there was a class in which Lorenzo went through that, and this is too valid also for linear networks. There is this equivalence between number of iterations and 1 over lambda. Okay. So this effect of implicit regularization is the controlling parameter there is for how long you're running gradient descent. The longer you run it is equivalent to a smaller and smaller lambda in your equivalent regularized problem. Okay, so if I want now to look beyond linear networks, of course, then I then in this case, if I take the gradient oops. So I wonder whether I can charge it with my phone, the pen. Oh, okay, but that should work. Thank you, thank you. Okay. So in this case, so that's a general least square, so square loss, but multi-layer case. Then these are the gradient descent equations and the Hessian there, with possibly this regularization term like before, that comes from a quadratic term in the loss. And so what happens here, if you look at, first of all, the gradient, is that without the regularization term, the gradient is 0 when the error is 0. But the Hessian in general would be degenerate. This will be again in general a rank 1 matrix, and I can show you in a second result. It says this is in general degenerate for deep RLU networks that are over-parameterized. and this we can say very little about it. So without the regularization term, this would be a degenerate minimum. Only that in this case we cannot really hope to use that gradient descent will converge to a good solution, like a minimum normal solution, because this is what happens around the zero of the gradient, and we cannot be sure that during gradient descent, directions that, for instance, are degenerate around the minimum may not be touched by gradient descent, as increased and so on during gradient descent. So the multi-layer nonlinear case is the one in which we really would like to have stationary solutions that are independent of the initial condition, non-degenerate Hessian. So the result about the degeneracy is something that Kenji Kawaguchi mentioned last time, proved, and it's in one of our memos. It's the Hessian matrix. In the case of zero error, will be over-parameterized. It will have in an over-parameterized network, we have zero eigenvalue, at least one. I'm not it's rather involved, but the intuition is pretty clear. You have many parameters. What I would like to be able to do here is the following. I'll be able to say that I can, using tools like derivatives and second derivatives, I would like to characterize the equilibrium point and the type of equilibrium point in this case in which the system of differential equation is nonlinear, because the network is highly nonlinear. Now, in order to do this, I have to look to use results that say under which conditions dynamical system can be described, nonlinear dynamical system can be described by their linearization. So around the intuition is around the minimum. What matters is really the linear approximation of the first terms in a Taylor approximation of the function close to a minimum for describing what's happening to the minimum. But there is a rather general result that is called the Hartmann-Grobman theorem, and proved probably 50 years ago or so. And this says that a gradient dynamical system can be described effectively in terms of its properties, qualitative properties, around an equilibrium by its linearization, if its Hessian is non-degenerate. And so this question of having in the gradient descent equation to be able to say that the Hessian is non-degenerate becomes also a powerful tool to say that I can use the linear type analysis using gradient and Hessian also in the nonlinear case, to be valid in the nonlinear case for networks that are nonlinear with a square loss. Okay, so see if now it works.
I can charge yours.
Yeah, I think I'll. Oh, wait. Now it works. Thank you. Okay, so there is an interesting question that I don't know the answer. I wonder whether any of you has some intuition. Suppose I have a landscape, a function of many variables. This landscape, even two variables, this landscape has, bottoms and peaks. It has valleys. And suppose it is a landscape that has some flat valleys. There are some critical points where the Hessian is degenerate. Now, suppose I add to this landscape a quadratic other landscape. Will the degenerate critical points disappear or not? I don't know the answer. By the way, functions that have no degenerate critical point are called Morse functions and play a very important role in topology and dynamical systems. There are also results saying that they are dense in the space of all continuous functions, because essentially if you have, say, a zero Hessian, if you have a positive Hessian, a small perturbation would not change the fact that it's positive. But if you have an Hessian which is exactly zero, a small perturbation will change it. So these are also called structurally stable or not. So I don't know. What about my question? If any of you has some intuition of the. Yeah. What is your?
It's going to be extra great if you do have an answer.
Sorry?
It's going to be extra great if you do have an answer. But you can improve.
Yeah, I sent a message to Steve's mail yesterday. Let's see if he answers, if he knows the answer. It was sometimes this subclass of this function are called the Morse-Smale functions. So, in one dimension, it's pretty clear that what I said is true. So, in other words, you will. So suppose you have a function that is missing the, it's a polynomial, one variable. You have a0 plus bx plus cx squared plus. Suppose I take out the x squared term. Now the Hessian of that is 0. The second derivative is 0. And so that function is not a Morse function. But if I now add a squared polynomial to it, it will be, again, a Morse function. So in the one-dimensional case, it's clear. In the higher dimensional case, I don't know. Sasha, any intuition? Okay. Okay. So, if you have this situation, I said in general the Hessian will be degenerate for, so the standard, the conclusion for the standard deep networks and the gradient descent or stochastic gradient descent you run on it is that you have flat valleys, degeneracy and dependence of initial conditions and an infinite number of solutions. Empirically, this seems what people find. Now, it's some way to fix it. If you add a regularization term, then what happens is that you have now the dynamical equations here. You have W dot equal to 0 when this is true, and you can make this error also pretty small, possibly, and in that case, it may be possible if all the En are small that this term will dominate and you will retrieve a positive definite Hessian. But we did not manage to find guarantees for this to be true. So it may happen or it may not happen. And this is related to this question I was asking, because if it were true that by adding quadratic term to the degenerate function to a known Morse function, you get a Morse function, then this problem would be solved. So I don't think it's the case. And so again, if you have known degeneracy because of the regularization, then you can say that if you have a positive definite Hessian at a minimum or stationary point of the gradient where your gradient converges, that would be have these properties for the nonlinear system, and you can say a lot of things about it because of Hartmann-Grobman, but if not, you cannot really extend these linear results to the nonlinear, to the nonlinear deep multi-layer networks, not even with the square laws. Now, with exponential losses, the situation is even, this was, by the way, let me just check one thing. So for this result about the degeneracy of the Hessian is Kenji Kawaguchi. So I'm just showing this for making the point that they did something a bit complicated. But let me go to the more interesting case of exponential loss, logistic cross entropy. Again, more interesting because it's what people mostly use, since deep networks are mostly used for classification. And in this case, the loss is sum of exponential terms. Yi is plus or minus 1. Again, let's look at first at linear networks of this type. So we have basically a vector, one row matrix of weights. And furthermore, let's assume that we have linearly separable data in this case. and this means that these terms yi f of xi with that f can be positive, so you are correct for all of the data points, right? So you say f of xi is negative when your label is -1, and is positive when your label is +1. So I get rid now of, under this assumption of the y term, and I'm looking at the dynamical system induced by the gradient, and this has this funny form of being the wij dot, the time derivative, is something like this. So this is positive, of course, and this may grow to infinity or to minus infinity, depending of the sign of this sum of the xj, of the x, for each component. If I use a vector notation instead of the matrix components, I have that w dot is this linear combination of the xn with these exponential terms. And on this type of dynamics, Cerebro last year had a quite interesting result, which is given by this mainly by this lemma. There are other ones. He had these results that the size of the weights increases to infinity as you iterate gradient descent. It is this w dash log t plus some other term that grows with time, rho, but in such a way that the limit of w and its norm, so the normalized vector there, that one is converges to the solution of the square loss hard margin, the hard margin SVM. So to the solution of the problem below, finding a set of weights that such that they separate the data and have minimum norm. So this result is pretty involved in terms of how it's derived. The intuition, well, we can see the intuition in a simple way here. The interesting point in this proof is that this this convergence, this point here, is independent of the initial conditions. So it's not like the gradient descent in the square loss case, in which you have convergence, but it's not a stable critical point. It depends on the initial condition. Yeah, it's independent of the initial conditions. So that's good also because it says that in this particular case, you have a control of the norm. You have a minimum norm here in a classification case, which is what Sasha would like to have. Right? The statement is that you are in a classification case, and the convergence of gradient descent is to a minimum norm solution in the, and so you have a control of the norm, which is what you want in terms of, say complexity, margin type bounds. This is in the linear case, exponential loss. So let's see. There is one, I will show you one variation of gradient descent that gives a proof, a simple proof of what Zrebro has obtained. But before doing this, we can check what happens if, in the case of the exponential loss, I add a regularization term, again with the idea that I may want to then look at the limit for lambda equals 0. And in this case, without regularization, the gradient descent, of course, you never find 0 of W dot unless you are at infinity without regularization. But with a lambda, you have a finite point at which you have 0 of the gradient. This would be when you solve for that equation for W dot equals 0, in which case you find this equation here. And there will be a W star which will solve that equation. And in fact, you find that W star, even without this assumption here, so W star here is a linear combination with positive coefficients, this exponential, of the data points. Okay. We know that during gradient descent, the magnitude of the W tends to increase, and so typically that exponential will be equivalent to a max operation. Will pick up the terms such that Wxn is minimum. So because this would be the terms with the largest value. In fact, this way of, say, summating terms having some coefficient in the exponent of the exponential becoming very large is one approximation to the maximum. But that's not so important for now, but that's the mechanism that makes this similar to support vector machines. This kind of maximum-like operation is what selects among all the data points, the ones that have the worst margin. Those are the support vectors. And the point here is that, as I said, W will be a linear combination of the data point. And so if I call, for instance, suppose that I call say X is the 1 over lambda, the sum of these terms xn. This will be xn here. And this I call it X, is some kind of average vector with those kind of weights. And then I have that W star will be equal to X um, and so in this case, I also find that the Hessian is going to be of this form. This form again has rank 1, but this part here coming from the regularization is a stable minimum. And so with an arbitrary small lambda, I get a positive Hessian, a stable point independent of initial conditions, and this seems to recover the cerebral result in a much simpler way. And I finish by showing a couple of simulations of this case. So this is the linear network exponential loss gradient descent, and if you perturb, you change the trailing error. Let's see. The red curve is not test. This is checking whether the function you get before and after the perturbation is the same that you had before. So we are doing this by having a separate test set and looking at the pattern of errors on this test set. If the function does not change, you should have the same pattern of error. Otherwise, the pattern of error may change. Not the quantity, just the pattern over which. Okay, so 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 I think the pattern of error is the blue one, and this is actually the percentage of error. So the pattern of error is a much more sensitive measure of whether you get the same function or not. And this is in the standard case, so it depends on the perturbation running. But if you have a regularization term, you perturb, and there is no change in the pattern of error apart from this small initial transit. So this gives you the independence of initial conditions. It also turns out that it performs better than the non-regularized case in this particular example. But that's a side point. Okay, so next time I'll conclude with a new algorithm for stochastic and gradient descent for deep networks, and also some more high-level thoughts about future problems in this kind of machine learning and theory and relations to what we know about the brain. So see you Monday.